All right, welcome back, everyone. So let's go ahead and continue with applications of the central limit theorem. All right, so the next part says, let's go ahead and use the central limit theorem. And the point I want to emphasize is you got to remember that the central limit theorem has three parts to it, which basically tells you that the center of the sampling distribution is the same as the center of the population, and that the variability of the sample mean distribution, the sampling distribution, is given by the formula sigma over square root of n, where sigma is the population standard deviation. Now, remember, there is a third part that if the sample size is large enough, then our distribution will be approximately normal. So make sure that whenever you see the words find probabilities and you're talking about the sample mean, you need to know the distribution of the sampling distribution. So it has to be normal. Otherwise, you're not going to be able to find probabilities. For example, when I took samples of size 10, the shape is slightly skewed right. So it's not exactly normal. So we want to be careful. So let's go ahead and continue with that Hollywood movie budget data set. So remember that the Hollywood movie budget data set pretends that we have information about all of the movies as well as the budget for those movies at a certain time. There are 1,056 movies in this data set, and we're going to pretend that that's the population. Here is the mean of the population as well as the standard deviation. So let's go ahead and just quickly record that. So for the Hollywood movie data set, we got that sigma mu is 51.379 and sigma is 57.927. So given that information, we're now gonna, they're now asking us, can you describe the sampling distribution of X bar? Whenever you see that word describe, you wanna produce the center, the spread, and the shape. So number one, let's get the center. So what is the center of the distribution of the sample mean gonna look like? Well, we recall that mu of X bar is simply equal to mu. So in this case, we see that the center of the sample mean is going to be 51.379. Number two, can we describe the spread or the variability of X bar? And that's given by sigma of X bar. And the formula was sigma over square root of n. So that's 57.927 divided by the square root of the sample size. In this case, it's 50. So we can go ahead and throw that into a calculator. For example, Desmos. We can see that Desmos here produces the value 8.192. And finally, number three, what about the shape? So if you remember, the shape of that population info is actually highly skewed right. Very highly skewed right. More or less looks like it's exponential. So anyway, we're asked, if you take samples of size 50, what would the shape look like? And again, we can simulate it, but notice I didn't simulate. I'm going to simulate after this. And because the sample size is 50, remember that our cutoff point was going to be 30. So we're going to check that off, and we're going to say that it's normally distributed. So I have not done any simulation, but I'm basically saying if I were to do a simulation, I can go ahead and tell you that the center is going to be 51.379. The spread is 8.192, and the shape is approximately normal. So we can go ahead and do that here. Right? Make sure you're looking at the Hollywood movie data set, and that you have sample size of 50. So let's generate a few of these samples. Let's go to 5,000. And take a look at the center. Actual center here for my simulation, 51.335 versus predicted 51.379. Spread is 7.9 versus predicted 8.192, pretty close. And my shape is approximately normal. So let's see, do you all think that this is approximately normal? I hope you're agreeing. All right, so notice no more need to simulate. We now have all the power by simply using the central limit theorem. All right, let's go ahead and do the next one. What is the probability? So that's the keyword right there. You want to find the probability that if you take a single sample of size 50, your sample mean. So now you're finding the likelihood of obtaining a sample mean. So this is literally saying, what's the probability that your sample mean will be greater than 65. I already have it typed up there, so let me put it over here. And like all problems before, when you have center, spread, and shape, please make a sketch of the distribution. So all of the stuff in light blue is theoretical. The theory right here says that my center is going to be 51.379, and my spread is going to be 8.192. So 65 is going to be somewhere to the right-hand side, about 2 standard deviations. So over here, 65. So here is the number line of the sample mean. And I want to basically see how likely is it that you're going to land above 65. So to find this probability, I'm going to use StatCrunch. So let's use the fact that there's a normal distribution. So I'm going to go to Stats, Calc, Normal, and make sure that this matches your paper. So my center was 51.379. And my standard deviation, remember that it's the standard deviation of this, of the sample mean. So it's 8.192. All right, and then I can go ahead and set this greater than 65. And what I want you to note is just make sure that this is the same graphic that you drew on your paper. If there's any difference, it could be that you didn't type one of these values in correctly. So the answer is 0.04818. So let's write that down. This probability 0.04818. All right, so there is our answer. This is the probability. Notice that it is actually less than 0.05. So this should actually be unusual. AKA unexpected for us to obtain if I simply take a single sample. So let me show you. Let me generate one sample. And notice that one sample that I generated has a sample mean of 53.568. So I landed somewhere over here. You take another sample. Now your sample mean is 40. So you can keep generating samples. And notice none of them are greater than 65, because that is an unusual event. It should not occur. Now, I want to go ahead and say this. Find the value that is 2 standard deviations above the expected value of mu of x bar. So this simply goes back to the idea of z-score. So 2 standard deviations. Remember, this is z equals 0. Z equals 1 is when you add 1 standard deviation. And so you need to go 2 standard deviations. So this would be that the z-score would be the center, mu of x bar, plus 2, because it's above, the standard deviation, which is sigma of x bar. So if you substitute that, you end up with 51.379 plus 2 times the spread, which is right here, 8.192. So we can go ahead and type that into Desmos just to determine that value. Remember, it was 51.379 plus 2 times 8.192. So you get 67.76. So 65 is slightly below 2 standard deviations to the right. All right, now let me go ahead and do part D, where it says compare your answer to the summary given to the right. So here's my summary given to the right. I only took 2,000 samples, and you can see how this area here is shaded red. And the reason for that is that that's the fraction of all sample means. So in red, you guys observe all of the sample means that are in fact greater than 65. And if you divide that by the total number of samples that we did, which in this case is 2,000, you get this proportion. So 0.066, that's fairly close to 0.048. So these are the values that you want to compare. They should be approximately the same. Obviously, this is a simulation. It means that the value will vary from point to point. And the answer gets better as your sample size increases. So here in this case, I have 5,000 samples. To get that, go ahead and click on where it says right tail. And you now get this picture here, and you click on this box at 67 where you can type in the cutoff value. For us, it's 65. And whoa, take a look at that value, 65. So if I cut off at 65 with 5,000 samples, the number of values, the proportion of sample means that are greater than 65 in this simulation is 0.048. 0.048. So the takeaway from this is we don't even need to simulate anymore because we simply go ahead and use the central limit theorem. And the central limit theorem, because it tells you center spread shape, then means you can simply go to the normal calculator to find probabilities. There is no more need for you to simulate. All right, so this is our first example. Please make sure that you rewatch this video to see the importance of the central limit theorem so that in the next problems you know what's going on. All right, I'll see you in the next one. Thank you.